everyone. Welcome to today's live broadcast, Glycomics and Glycoproteomics by CESI MS for biomarker discovery and biopharmaceutical characterization. I am Brenda Kelly Kim of LabRoots, and I'll be your moderator for today's event. LabRoots.com is the leading scientific social networking site, and we are proud to bring you this interactive web seminar. For more information, please visit us at LabRoots.com. This webcast is kindly sponsored by SCIEX. SCIEX's global leadership and world-class service and support in the capillary electrophoresis and LC-MS industry have made it a trusted partner to thousands of the scientists and lab analysts worldwide. For more information, please visit us at www.sciex.com. Here's how this presentation works. We want to hear from you. Questions, comments, and even answers can be submitted via the green Q&A button at the lower left of your screen. We'll try to get to as many of your questions as we have time for, and if not, we will make sure to follow up with you by email. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you can't hear or see this presentation properly, please let us know by clicking on the support button at the top right or the Q&A button in the lower left. I would now like to introduce today's speaker, Guinevere Kammeijer. Guinevere Kammeijer received a BSc degree in Biotechnology Forensic Sciences from the University of Applied Science, Van Hal Larenstein, Leeuwarden, followed by an MSc in Analytical Chemistry at the BU University Amsterdam. The MSc included an internship at their Center for Proteomics and Metabolomics at Leiden University Medical Center, where she focused on small-scale sample preparation with CESI MS. Currently, she is a PhD candidate at the same Center for Proteomics and Metabolomics under the supervision of Professor Manfred Wöhrer. Her project involves exploring CESI MS for protein glycosylation analysis, with a focus on the analysis of glycopeptides employing a porous nanosprayer for MS coupling. I'll now turn it over to Guinevere for her presentation.
Thank you, Brenda, for this kind introduction, and thank you all for tuning in today. Before I go really in-depth in what my research is, I first want to briefly explain what is glycosylation. Glycosylation is one of the highly prevalent co- and post-translation modifications that are out there, and it's thought to be the most complex type. They're known to be really heterogeneous, and more than 50% of the human proteins are known to be glycosylated. It has a large influence on the protein function, and for example, you can see here on your right side, the protein prostate-specific antigen, and you can see that the protein itself is not really big, but if you look closely, we also observe a glycosylation site. And here you can see that the glycan plays a big part of the protein, and therefore you can imagine that plays an important role in the protein function. We also know, looking at biopharmaceuticals, that these glycans can really affect the physiological conditions and also the effect of the biopharmaceutical itself. For example, if you have sialic acids at the end of your glycan chain, they might have a longer half-life compared to those biopharmaceuticals that don't have the sialic acid attached. So therefore, it's really important to do biopharmaceutical characterization. Looking at the glycans and how they're built up, there are 7 most abundant monosaccharides in humans, displayed over here. And as you can see, the first 3 ones, the glucose, the galactose, and the mannose, they share the same mass, so they're isoforms. As well, for the N-acetylglucosamine, N-acetylgalactosamine, we can also have the red triangle, which is a fucose, and we can have one of the sialic acids, which is known as N-acetylmuraminic acid. Looking at these monosaccharides, we can build our glycans as we have our amino acids to build our protein. And we can display them like this, but this is not really easy to interpret and see what kind of monosaccharides are attached to each other. So most of the time we would like to display it more easy to see, and this is how we display it. And if we look at end-link glycosylation, because my research is mainly focused on end-link glycosylation, there's one sequence that we should follow looking at the protein. So if we have an asparagine followed by any amino acid with one exception, and that's proline, followed by serine or a threonine, we can have a possible ending glycosylation site. And as I already said, these glycans can be really heterogeneous. So we try to divide them in 3 types, and as you can see, they're displayed over here. They all share the same common core attached to the asparagine. So we have the 2 blue squares followed by the 3 green circles. And these are the cores to build our glycans. But the first type has only the green circles on top, and that are the mannoses. So we like to call them high mannose types. Then the middle one is a little bit more complex. So we have more different monosaccharides attached. We can have a core fucose, for example. And in this case, we call it a complex glycopeptide. We can also have something in between where one antenna is mainly high mannose and the other one is a complex. So that means that we have a hybrid type. And these are 3 different glycotypes that we can have with end-link glycosylation. But why is it really important that we do analysis of glycosylation? And that's due to the fact, as I've already mentioned previously, it can largely influence the protein function. So it can influence the protein-protein interaction. It can also play a role in recognition, signaling, trafficking. But we also know, looking at glycosylation profiles, that they can be really age-dependent. How older you get, how differently your glycoprofile will look. But we also know that it can change with disease. So this is all rather interesting to see, but how can we analyze glycosylation? Well, one of the things that we could do is insect native glycoprotein analysis. And what you can see here we have our native form, and we have multiple end-link glycosylation sites. And doing this analysis, the benefit of this is that you can have really multiple isoforms and analyze them. But if you want to know which glycan is attached to which site, you will not be able to detect that. And the same counts if you look at the intact denatured glycoprotein. The same effect, we still don't know which glycosylation is occupied because it's really hard to see in your analysis what's going on. We can also have another way to look at it and just look only at the sugars. The advantage of this one is that you can cleave off all the sugars of many different glycoproteins, so you can analyze a really complex sample, for example, plasma. In this case, you use an enzyme that cleaves off all the sugars, and at the end, you only have the glycans left in your analysis. You can analyze them, but you lose all information about which glycan was attached to which protein, and especially which site was occupied. So these are things that you need to take into account when you do the analysis. But if you really would like to have site specificity and protein specificity, you might consider to do glycopeptide analysis. In this case, you use an enzyme to cleave your protein into pieces, for example, tryptic digest. And with this, you produce many different peptides and glycopeptides. And in this case, you have unique peptides that are corresponding to your protein. And with that, you get protein specificity and site specificity. However, you will gain a lot of information and your analysis will be rather difficult. So as a summary, how you can analyze glycosylation, we can have 3 different approaches. So we can do intact, where you can detect the different isoforms. It's really protein specific. However, it's not site specific, and you really need to have an isolated protein. For glycopeptides, you gain the information about site specificity, protein specificity. However, you need to take into account that you have a fast increase of the complexity of your data, and it can take some time to really go in-depth in your data. For the release glycans, you might want to use if you really have complex samples, and you don't really care about the site specificity or the protein specificity, you just want to see a glycoprofile. And in this case, you can use the release glycans. In my research, I mainly focus on glycopeptide research, but we also just recently started to explore the possibilities with CESI MS using release glycans. The outline of my presentation today is that I would like to tell you something about biomarker discovery, then a method development that we have performed, and see how that method development compares to other analytical platforms. And at the end, I would also like to briefly touch the part about the Glycomics study that we just started up. So regarding the biomarker discovery, I would like to focus on prostate cancer. As you might know, the prostate is positioned over here, and if you have prostate cancer, there are many different stages that you can have, as with the other cancers that are out there. However, if there is a suspicion for prostate cancer, they will have a look at prostate-specific antigen, which is a protein that's produced in the prostate for semen. So if you look at the normal situation that we have a prostate and we have a blood vessel. And in our prostate we have some PSA. And sometimes in normal situations, some of this PSA can leak into your blood vessel. But now we have prostate cancer, and the hypothesis is that the cells are really disaligned and there are bigger gaps, and therefore more PSA can leak into your blood vessel, and that's why they use the PSA for screening. So this is the current clinical research that they use. So there's prostate cancer, there's a suspicion if you might have it, so they will perform a PSA test. Then they will perform a digital rectal exam, followed by a biopsy, and if you are already in a high stage, you will also get a bone scan. But today I would like to focus on the PSA test. The PSA test is a procedure where they collect your blood and determine the amount of PSA in blood. And if it's above 3 nanograms per milliliter, all alarm bells go off because high values of PSA can be caused by prostate cancer. But that's not the only thing that can cause high values, because the prostate can also just be enlarged, it can be inflamed, and also if you're getting older, also your PSA value will change with that. Furthermore, we need to take into account, if we do the PSA test, we can't distinguish between benign and malignant. So those are all things that we need to take into account when we're doing the screening for prostate cancer. We also need to take into account that 1% of the men with a PSA value below 3 nanograms per milliliter can still have prostate cancer. So this already shows that the PSA test is not really bulletproof. And this was even further shown by a study in 2012, where they investigated 1,000 men over 10 years, and they had an interval from 1 up to 4 years. And the results were rather interesting. So 22% got a positive result in prostates with the PSA test. 11% of that was a false positive, and you need to imagine that all these males will get a positive result, they get scared, they might have prostate cancer. They will go to the procedure, they will get biopsies, and at the end, it appeared that they had a false positive. Also, 11% indeed had prostate cancer, but 5% of them got complications during the treatment. And you need to imagine if they get a biopsy, maybe they get an antibiotics cure, but maybe they're resistant to the antibiotics, so there are a lot of different things that can happen during the treatment. And they saw that 0.4 to 0.5% still died even though there was an early screening of the PSA test. And only 1 male person was saved by using the early screening of PSA. And this really started the discussion in the US if we really need to do PSA screening, because it's not really bulletproof, as I've already said. We scare more people than we really save with the screening test. So we thought, okay, maybe let's have a look at PSA. So this is the protein sequence, and as you can see, there have 5 disulfide bridges. You can also really nicely see in this figure the prostate-specific antigen. And if you look closely to the protein sequence, you can see that there's a possible end-link glycosylation site. And that's also illustrated in the figure that there might be a glycan site. So we thought maybe we can analyze the glycopeptides in this sample and see how the glycoprofile corresponds to that. So what we did, we reduced and alkylated our sample and performed a tryptic digest. If you do a tryptic digest, you will cleave off the arginine and lysine, and that means we will have a really small peptide backbone if we have a complete cleavage. So we only have a peptide backbone of NK. We wanted to analyze this with CESI MS. So CE is capillary electrophoresis, where we separate our ions based on electrophoretic mobility by using an applied voltage. then we use the electrospray ionization to introduce the protonated ions into the mass spectrometer, where we can sort and separate the ions according to the mass and charge in vacuum. So as you can see is that the CE and ESI part are merged into one, and that's due that we're using this technology, the CSI technology. And it's a little bit different than if you compare it to sheet-less or sheet-liquid interface, because in this case we have our separation capillary, and we also have a conductive liquid capillary that's filled with 10% acetic acid. And what we do with that, we have our separation capillary, the end of our tip is made porous by etching it with an acid, and that makes it permeable to interact with the conductive liquid that is surrounding it. And that's how we keep our closed circuit, because in CE it's really important to have a closed circuit to have a stable migration and a stable spray. So that's what they have done with this invention, and it works really nicely. And compared to sheet-liquid interface, we can maintain really low flow rates. And as an advantage compared to sheet-liquid, as we don't really dilute our sample anymore, we get an improved resolution and really high sensitivity. So that's the CSI technology that we are using. Now something about the analysis of tryptic PSA. So what you can see here is the base peak electropherogram, and we didn't really purify our sample. We just took a standard, reduced and alkylated, did a tryptic digest, and directly analyzed it on the CESI MS. And what we have here in a base peak electropherogram, we have many different peptides and glycopeptides corresponding from PSA. But looking a little bit more closely, we observe 3 different clusters if we only look at the glycopeptides. So we have cluster A, B, and C. And if looking at cluster A, we can see that we have many different glycopeptides, but as you might observe is that there are no sialic acids attached to these glycopeptides, so no purple diamonds. Also, what you can nicely see over here is that if you take, for example, one moment, this glycopeptide, I hope you can see that I'm using this one, and if there's a fucose attached to it, you can see that the migration is a little bit later, so we really separate on which monosaccharide is attached to our peptide backbone. So moving further on to cluster B, it became a little bit more interesting. So in this case, we did extracted ion electropherograms of certain masses of our glycopeptides. And if you look closely, we observed 2 peaks for the same M over Z value. And if you looked a little bit more in depth, in the profiles, our MS2 looked exactly similar, so fragmentation-wise, both peaks showed similar results. Isotopic pattern was completely the same. But still, we observed 2 peaks, so there was a migration difference. However, for this glycopeptide, we only observed 1 peak. And then again for this one, 2. And again for this one, 2. So that made us wondering, why do we observe for some glycopeptides 1 peak, for some of them 2 peaks? So we thought, okay, let's have a look at cluster C. So in cluster A, we only have the glycopeptides without a sialic acid. In cluster B, we have them with 1 sialic acid. And in cluster C, we observe the glycopeptides with 2 sialic acids attached to the glycopeptide. And here, we observed even 3 peaks popping up at the same M over Z value. And then we had a look for this one, and again 2. And then we had another look, and again 2. So taking this all into account, we started wondering what is going on. And then we thought, okay, it really looks like it's dependent on the sialic acids, why we have a different immigration and different peaks popping up. So it might be that we have linkage separation. So looking at this, if we have this glycopeptide, we know that we can have 2 different linked sialic acids. We can have alpha-6 linked sialic acids or alpha-3 linked sialic acids. And taking that into account, that means that we could have 3 different possibilities, so 3 different isoforms. And that could explain why we have three different peaks. So we want to investigate this. And we already have a nice in-house method where we release our glycans with PNGase F and perform ethyl esterification, and then we analyze it with the MALDI tool. So this method is really nice because we can distinguish between alpha-3 and alpha-6 linked sialic acids. If you want to know more about the ethyl esterification, I would like to inform you that there will be a pop-up, a new window that will pop up in your screen with a link to this paper where it's nicely described. And what you can see with the ethylated version, so alpha-6 will ethylate, and the alpha-3 will lectinize, and that means you will lose the water. And that means also that we have a difference in mass, and that's why we can distinguish between alpha-3 and alpha-6. So let's have a look at the results of the MALDI profiling, and we got a really nice spectra out of it. However, as I've already said during the introduction, if you do a glycomic study, it might be that you're also releasing sugars from other proteins that are in your sample. Of course, you assume that you have a pure sample if it's a standard, but it might be that there's still some contamination going on. So just recently also a new method came out. Also this one will pop up in a new window with a link to the article, where we perform a tryptic digest and then perform demethylamidation. And also in this case, we're able to distinguish between the different linked sialic acids. To make it a little bit easier to see, these are the 3 isoforms. They should have the same composition, but the sialic acids are differently linked. And that's what we nicely see in the MALDI profiling, that indeed we have the 3 different linked sialic acids. However, if you look to this glycopeptide and the 2 isoforms, we only observe 2. And that's due to the fact that the sialic acids attached to the yellow square, we can only have alpha-6 linked sialic acids. So that means that that one is fixed. However, the purple diamond, the sialic acid that is attached to the galactose, so the yellow circle, can still be differently linked, alpha-3 versus alpha-6, and that's why we have 2 isoforms. And at the end, with the MALDI profiling, we could identify 34 glycans and 38 glycopeptides. So we were already quite happy with the results. And comparing the MALDI profiling together with our CESI MS, we thought, okay, let's hope that our ratios are really similar, and then we can assume that the most abundant one is fully alpha-6 sialated species. Then we have a mixture of alpha-3 and alpha-6, followed by the one that's fully alpha-3 sialated. And if this is the case, we can test that with an exoglycosidase using Streptococcus pneumoniae, and this will cleave off only the alpha-3 linked sialic acids. So cleaving off alpha-3 linked sialic acids means that this peak should disappear, because you have only alpha-3 linked sialic acids attached to your glycopeptide, and if you cleave them off, you will have a glycopeptide without any sialic acids. And that means that that glycopeptide should move to the first cluster in our electropherogram. Then also, this peak should disappear, because we have one alpha-3 linked sialic acid. That one should be cleaved off. The alpha-6 remains, and that means we have only one sialic acid left to our glycopeptide, and that means that that one should move to cluster B. And then the fully alpha-6 sialated species should remain. So we performed this, and what you indeed can see is that in panel A we have it before the treatment, and in B you can see after treatment, and we really diminished the alpha-3 sialated glycopeptides, indicating that we might indeed have the linkage separation. So, but why is sialic acid linkage important? Why is it beneficial that we can do this without any further sample prep? Then we need to have a closer look at the sialic acids, because they can serve as a binding site. They're at the end of our glycan chain, so they can interfere with lectins, toxins, and pathogens. But also we know that alpha-3 and alpha-6 can have different values. So alpha-3 is known to be more involved in the metastasis for several types of cancer, while alpha-6 is known to block galectin binding. So therefore it's really important to know what kind of linkage you have going on your glycopeptide. So let's again have a look at cluster C. So first of all, we were able to identify 4 glycopeptides. And now we can identify all the different peaks in our electropherogram. And now we were able to identify 10 different isoforms in this sample with a disylated species. And at the end, we were able to identify 65 glycopeptides. So if you compare that to what we saw in the MALDI profiling, we're a little bit more sensitive. We could identify roughly more than 25 glycopeptides more compared to the MALDI-12 method. But we weren't really done with the linkage separation. So we want to explore it a little bit further. And what we did, we took a biopharmaceutical, a monoclonal antibody, from which we know that if it has sialic acids, they can only be alpha-3 linked. We also took a polyclonal antibody, from which we know it can only have alpha-6 linked sialic acids. And what you can see is that the glycopeptides without the sialic acids really migrate at a similar time. However, the sialic acid species have a difference in migration, alpha-3 versus alpha-6. So you might discuss that it could be an alignment issue. So what we did a co-injection of both analytes. And indeed what you see nicely over here is that we get baseline separation of these different linked sialic acids. However, the ones without the sialic acid migrate really exactly at the same time. But then we started wondering, okay, so we probably have a separation based on the linkages of sialic acids. But what is the reason behind it? So of course we're doing CE, so we thought maybe it has to do something with the pKa of our sialic acids. Maybe there's a slight difference between the pKa's. So we thought, let's have a look. So general pKa of sialic acids, what we could find should be around 2.6. And you should know that our background electrolyte that we use is 10% acetic acid, which should have a pH of 2.26, so that's close in the proximity of our pKa. So if there's a slight difference, it might be that the one is a little bit more protonated than the other one. So we want to investigate that. However, in our lab, we didn't really have the tools to do that. So we went to the University of Geneva, where they were able to determine the absolute pKa value of two standards, alpha-3 linked sialyl lactose and alpha-6 sialyl lactose. And what they basically did is they injected the compounds together with an EOF at different pHs. And with that, they could determine the limiting mobilities and the effective mobilities. And what they could do with that is kind of make a titration curve, and from that determine the absolute pKa value. For alpha-3, they could determine that at 1.78, and for alpha-6 at 1.84. However, as you can see, the confidence intervals overlap. So that was a little bit of a pity for us. So we thought, okay, we can do many more experiments and see if we can get the confidence interval lower, or we can maybe try a different approach. And that's what Julie Schappler did for us. And what she did, she tried to do a different method, which is called internal standard CE, and where they inject the compounds together with an EOF at two different pHs. So the compounds are injected together, and as a result, they did 3 experiments for us. So they tried to predict the value in silico, but also over here you can see that the confidence interval really overlaps. Then the absolute pKa value, where also the confidence interval overlaps. But with internal standard CE, they could define the relative value, and they found a difference of 0.032 between the different pKa's. So that's rather interesting. However, it's really small. So we thought, can this small difference really cause such a big migration difference of roughly 1 minute? So then we need to have a look at this formula, where you can define the effective mobility. However, we already had the effective mobility, so we could arrange this formula and make it more comparable for our own methods. So we could define the effective length of our capillary, or total length of our capillary, and the voltage that we apply. So doing that and having our effective mobilities of the different linked sialic acids, we could determine that the migration time for the 2,3 should be around 36.25 minutes, Or for the 2,6, it should be around 35.24 minutes, showing that indeed the small difference in pKa can really show a difference of 1 minute. So we were really happy with these results. And to conclude a little bit our research for biomarker discovery, I hope that I could show you that using CESI MS, you're really able to retrieve a lot of information. You can go really in depth, you can easily do fragmentation, and you also only need minor sample prep. You only need to reduce an alkylate, do a tryptic digest, and then your sample is already ready to be analyzed. And if we look at the separation mechanism, we separate based on which glycan is attached. If there is a different monosaccharide, your migration will be different. But also, as I show, we can separate the different isoforms of the sialic acids, alpha-3 versus alpha-6, where we get nicely baseline separation. And if we look a little bit more closely, as you might remember, we have 3 different clusters. So we separate based on the charge. So if you have more sialic acids, it becomes more negatively charged, so it will take longer for them to migrate off from our capillary. And if I need to name a disadvantage, I would say the disadvantage is that it, at the moment, is not really high throughput. It's 60 minutes per sample, but what you get in the return is baseline separation, really in-depth information. So these are things that you would like to consider. Now I would like to move on to the method development. So for the method development, there was this product put on the market, and what they used with this product, they used analysis of glycopeptides with nano-LC-MS, and the product is a dopant-enriched nitrogen gas. And what they observed with the analysis of glycopeptides using this dopant-enriched nitrogen gas is that they got an increase in sensitivity. So maybe you're not familiar with this product, so I will just briefly explain it. You have a bottle with a dopant in there, so for example acetonitrile. Then you have our nebulizer gas, in our case nitrogen gas, coming into our bottle, and it mixes together with the ACN, and at the end you will have a dopant-enriched nitrogen gas, which you can introduce into your ESI source. And they saw for glycopeptides that they got higher charge states, and also that they got an increase in signal intensity. And overall, 1 order of magnitude was found as an improvement factor. So that was really interesting. So we thought, is this applicable for CESI MS? However, there was one issue. We don't really use a nebulizer gas with our current setup. So what you can see is our source over here. And there also is our capillary attached to the source. And if you look a little bit more closely, what we see is that there's a cone surrounding our capillary. And that's how we attach our dopant-enriched nitrogen gas, because at the end of our capillary, we were able to use to attach dopant-enriched nitrogen gas, which now can flow coaxially together with our spray. So here is just a magnification where you can really nicely see that this polymer cone is just surrounding our capillary. And as a first result, what we saw, so in panel A you see the CESI MS without DAN-gas, and in panel C you see the one with DAN-gas. And what you can easily see, so this is just the background. And if you're looking at the background, we had an overall lower background. And you can maybe imagine that this can really enhance your signal-to-noise ratio. So we want to check that with a standard that we have in our lab, protocol and IgG. And first of all, we want to make sure that the relative values were not skewed. So we had a look at the 10 most abundant glycopeptides, and we compared CESI MS against CESI MS with DAN-gas. And as you can see in panel A, we really got similar results in the relative ratios. However, looking at the peak area or the signal to noise, we really got an increasement in sensitivity. So also, let's have a look at the charge states. For this glycopeptide, you can see if you use CESI MS without DAN-gas, you mainly see triply charged species, a little bit of doubly charged species, and a lot of background. So if you look at panel B, where we use the DAN-gas, we mainly see triply charged species, but also quite a lot of quadruply charged species, and we don't observe any of the doubly charged species anymore. So what this basically means is that indeed also with CESI MS, we move to higher charge states using this then gas. And also it's interesting to know because if you have glycopeptides that are even more complex than is illustrated with this one, you have more sialic acids attached, it might be that that glycopeptide, the doubly charged species, will move outside of your detection window. So this could be really beneficial for really complex samples, complex peptides. Also, we had a look at PSA, also different glycopeptides, and in this case, similar results were obtained. Relative peak area was similar, however, there was still an increase in signal to noise and also in the peak area itself. So that was the method development, and we thought, okay, it looks pretty nice, we get higher charge states, higher sensitivity, but how does it really compare to the different analytical platforms that are already out there for glycomics analysis? So first of all, we want to compare it to nano-LC-MS. And we want to compare it to nano-LC-MS because we thought it's the most fair comparison to make because nano-LC is also a microscale separation technique. And as it's also microscale, we also have the same mass spectrometer behind it in our own lab. So we thought that's the most fair comparison that we can make. So this was a study in 2013, and what you can see is that nano-LC-MS basically only separates on the peptide backbone. So we had IgG, we analyzed that, and there were 3 different subclasses, IgG1, IgG4, and IgG2. And you can really see nicely that all the IgG1 subclass glycopeptides were really eluting at the same time. However, looking at the CESI MS, the peptide backbone doesn't really have a big influence. We more separate on which glycan is attached. So we separate if there is a G1F, a G2F, or G0F. So how many galactoses, for example, are out there. And we even get a better separation if we have a sialic acids because that one migrates even furthermore. But what they already saw is that in 2013 that CESI MS was really more sensitive looking at the samples. So we thought, how does it now compare to this then gas? So we set up an experiment to determine the limit of detection, comparing nano-LC-MS versus CESI MS with and without then gas, and we analyzed a biopharmaceutical monoclonal antibody. And we had different dilution factors varying from 0 up to 5,000, and then we used it on the nano-LC-MS. We injected 1 microliter because that's our standard method out there. And we also analyzed on the CESI MS. We injected only 44 nanoliters. But what you also can see is that the concentration is a little bit differently. And that's due to the fact that we're doing an online pre-concentration step, which is called transient isotachophoresis. And with that, we need to add a leading electrolyte. And that's why our concentration is slightly different than the one from nano-LC-MS. Looking at the results, we have a high concentration, middle concentration, and a low concentration of this glycopeptide, this G1F. You can see that CESI MS and CESI MS with then gas are really more sensitive if you just look at the absolute peak areas. Also, what was interesting for us to see is that if you look at cluster C, we were not able to analyze this glycopeptide with a signal-to-noise above 3 for nano-LC-MS measurements anymore. But for the CESI MS, we were still fine, and especially the one with then gas. So we could summarize that, and what we saw was for nano-LC-MS, we could determine the minimal concentration of IgG that was needed, and that was 250 picograms per microliter. Then we also compared it to CESI MS, which was 75 picograms per microliter, and with then gas, we could trim that even down to 3 picograms per microliter. And for us, I think that was the most interesting fact to see, because looking at the limit of detection of the glycopeptides, we already kind of knew that we were more sensitive compared to nano-LC-MS, but the CESI MS with then gas really showed that if you look at the concentration, we're a lot more sensitive than nano-LC-MS, and that could be really beneficial. Because most of the time when people ask me why you're doing CE analysis while you can do nano-LC analysis, they say concentration-wise it doesn't really matter. So just use nano-LC-MS. And now I could prove with this method we have way better sensitivity and also concentration-wise. So I think that's an important message that we could take home from this. But we also want to validate it to other analytical platforms, and we took the golden standard, helic fluorescence of 2AB labeled glycans. And what we did, we analyzed the sample 6 times on 2 days, and then also compared to MALDI MS and nano-LC-MS. And this was the result. So again, the biopharmaceutical monoclonal antibody. And dependent on the method, we saw glycans are glycopeptides, but just looking at the 5 most abundant glycans or glycopeptides, we really observed similar relative ratios. And it looks like that the CESI MS fits perfectly in line with this. Also, looking at the lower abundant species, we still see that CESI MS, so that's the first bar graph, really fits in nicely. There might be a little bit of skewing if you look at the sialic species, but overall, I would say CESI MS performs as well as good as the nano-LC-MS measurements. And it really shows that we could do quantitative analysis using CESI MS and the DENGase. Because we also performed inter- and intraday repeatability tests. So this was the outcome. We analyzed the sample 6 times on 3 days and just had a look at the 3 most abundant glycopeptides. And we also varied with the dilution factor, so we went from 5 times diluted up to 500 times diluted, which is close to the limit of quantitation. And what you can nicely see is that the RSDs are below 4%. And we were really happy with these results. So you can perform relative quantitation using CESI MS with really good RSDs. So as a summary of this method development and comparing it to other analytical platforms, I hope that I could show you that using this DENGase really enhanced our sensitivity and repeatability. There are limits of detections. We defined that concentration-wise, also CESI MS can be way more improved using this DENGase. And it's a nice complementary technique for other analytical platforms that are out there. And showing with the inter- and intraday repeatability, we really can do relative quantitation using this CESI MS. So now I would like to focus on the glycomics part. So as I said, we just recently started up this project, so the data is really fresh, but I'm really happy that I can also share it today with you. So we wanted to figure out if we can analyze glycans in positive ion modes using CESI MS. So we took a sample, again the biopharmaceutical, and we released the sugars by using PNGase F. And if there are sialic acids attached to our glycans, that means they will be more negatively charged than positively charged. So we want to get rid of that charge. And what we did, we performed the demethylamidation, which was mentioned previously, where we can also distinguish nicely between alpha-3 and alpha-6 linked sialic acids. Then we purified and enriched the sample, and then we labeled it because we want to have a positive charge. Overall, the glycans are neutral if there are no sialic acids attached, so you want to have the positive charge to it. And we use for that diaminopyridine, Giroir reagent C, or Giroir reagent P. And then we purified and enriched the sample again. And what you can see in this analysis of the CESI MS, so we analyzed dimethyl amidated monoclonal antibody labeled with Giroir reagent P. We could get a nice base peak electrophoregram. It looks really clean, but if you look more closely in the section where it's the red square, we observe a lot of different glycans. So what we can see here below is the 2 most abundant glycans, but if we look at the lower abundant ones, we were still really capable of analyzing a lot of different glycans in this biopharmaceutical. But just to compare the different labels, we put it out like this. And here you can also nicely see that all the labels were rather consistent in their relative ratios between the different glycans. So this was really promising and showed us that we can indeed do CESI MS and glycan analysis. But then we want to take a little bit a step further, and we thought, okay, maybe we can define the limit of quantitation using CESI MS and Glycomics data. So we want to have a look at total plasma in glycom because that's a well-used method in our lab where we do glycoprofiling of the full plasma. So we had some plasma, we released the sugars again, then we performed again the demethylamidation, and then we purified and enriched it, and then we analyzed it on the MALDI. And we did that due to the fact that's the normal method how we analyze the glycans from plasma. Then we took the same sample, labeled it with urate P, and then we purified and enriched it again and measured it with the CESI MS. So this was how we want to determine the limit of quantitation. So we had different dilution series. Again, it was rather similar setup as with the nano-CMS part. So for MALDI MS, we need to spot 2 microliters onto our plate. For CESI MS, we still injected 44 nanoliters, and our dilution factor varies from 0 up to 100. And also in this case, you can see that the concentration is a little bit different due to the fact of adding a leading electrolyte for CESI MS measurements. However, to really make a criteria what we want to see for the limit of quantitation, we said, okay, we still want to see the 26 most abundant glycoforms that are present, and we want to see them with a signal-to-noise above 9, and a ppm error should be below 5. So this was the result that we got for CESI MS. So you can see here the different dilutions, and they're rather consistent. However, looking at the most abundant ones and at the more complex types, so more on your right side, you see that there's some skewing going on. And we assume this is mainly due to some saturation effect into our mass spec. And as I said, these data are really preliminary, so we need to look a little bit more in depth what is exactly going on. But we were still happy because if you look at the average RSD shown in this table for the different dilutions, we could find the average RSD of the 26 glycans for 50 times diluted below 8%. And I think for limit of quantitation, this is really promising. So we could go up to 50 times dilutions using the CESI MS. And what you can also see is that if you look at the concentration and how the different glycans perform on that with the area under the curve, you can see for the high mannose type with 0.3% that we got a rather linear response. And the same counts for the sialated species with 3 sialic acids. However, the most abundant one, so the left top corner, you can see that it's a little bit less linear, and this could be due to the fact that we have our saturation effect going on. So that's still something that we would like to investigate, but we're already quite happy with these results. So comparing MALDI MS with CESI MS, we could make a fair comparison, we believe. So for MALDI MS, we could only go to 2 times diluted. Well, for CESI MS, as I said, 50 times diluted is as far that we could go. The relative ratios look rather similar. It's a little bit differently, but overall it looks pretty okay. And this is just the summary. So we could define 2 times diluted for MALDI MS, 50 times diluted for CESI MS. And that makes that CESI MS using the then gas is 44 times more sensitive in concentration compared to MALDI MS. And I think that's a really interesting message, because how often do you analyze something with your MALDI MS, you don't really get enough sensitivity and not enough intensity with your analysis. And in this case, you might want to consider to just take your sample, label it with a positive label, and analyze it on the CESI MS. Also, we could determine the theoretically limit of quantitation to reach signal-to-noise, and for MALDI MS, this was on average per glycan 16.6 femtomole, while for CESI MS, we could trim that down to 1.3 attomoles. So this is also good to know if you want to do some analysis, that you are still able to analyze that. So as a summary, I would say glycan analysis with CESI MS is possible. Only you need to derivatize your sialic acids, and you need to add a positive label. And for us, the most interesting fact was that CESI MS is found to be 44 times more sensitive in concentration compared to MALDI-12 MS measurements. So now I come to the end of my presentation, and as a perspective for what I have shown you today, for the biomarker discovery, as I showed, currently cancer diagnosis is really dependent on the concentration of a certain protein in plasma. And it's not really always specific enough to really conclude anything out of that. And we believe that a glycoprofile could be a way more specific biomarker for this. And we think using the CESI MS, we have enough sensitivity and specificity to really figure this out. We only need minor sample prep. However, of course, this should be tested with cohorts, and that's currently what we're doing. We're analyzing some prostate cancer patients and see if we can define a more specific biomarker using a glycoprofile. And hopefully soon I can show you some results about that. For the method development, of course, we never really stop with optimization, so we're always looking if we can optimize it somewhere else. For the different dopants, it might also be interesting because we use now acetonitrile, but it could be that different dopants can also have different effects and maybe even enhance furthermore. And all of our research, we would like to try to analyze our samples on neutral capillaries and see what the effect of that is. For the glycan analysis using CESI MS, we could still improve in our sample prep because we have now 2 purification steps, so that maybe can trim down maybe a little bit less of an incubation during the labeling process. And also we would like to explore the possibilities for different labels. So we have now 3 different labels tested, but there might be many different labels out there that we could use. And at the end, we would also like to see if we can go to negative ion mode, because this could be really, really beneficial, because you don't need to stabilize your sialic acids anymore, because this can only aid in the migration of your glycans. And as you might know, in the biopharmaceutical industry, HCS-labeled glycans are already well known and well used using CE. So it would be great if we can use the same sample, the same CE, and just couple it to mass spectrometry to gain a little bit more in-depth knowledge about our samples. Of course, I couldn't really do all the research only on my own, so I would like to thank all my dear colleagues at the Center for Proteomics and Metabolomics, and especially Noortje de Haan for helping me with the glycan analysis, Isabel Kohler and David Falk for helping me with the dengue gas, and of course my promoter, Manfred Roer. Also, I would like to thank our collaboration together with the Academic Medical Center, where we get our cohort fixed for prostate cancer research. And of course, University of Geneva is thanked for helping us out with the PKA determination. I would like to thank Astellas and IBD Biome for funding us, and especially Sykes, not only for funding, but also helping me to present my data and get it really out what we're doing. So with that, I would like to conclude and thank you for your attention. And if you have any questions, feel free to ask them.
Thank you for that presentation, Guinevere. Lots of good information there. Before we get to our question and answers, I want to let our attendees know that they will be seeing a polling question appearing on their screen momentarily. If you could take just a little bit of time to answer this question so we can bring you the most relevant information possible, we sure would appreciate it. We want to get right to questions and input, so let me remind our audience how to let us know what you had to say. Questions can be submitted via the Q&A button at the lower left. We're going to try to get to all of you, but if not, we will be sure and follow up after the broadcast. I see that we do have a question coming in already. An attendee says, great talk, thank you. Regarding the elucidation of glycostructures in PSA, was this performed using a standard material or a human sample? How much material, volume, and concentration do you need for such an analysis?
Yeah, that's a great question. So what I bought a standard, but it's from human material. It's PSA was captured from semen, and we just bought that. And we took that as a standard. And for the CE analysis, what we really use as an injection is only 1 nanogram. That should be already sufficient to get enough of our glycoprofile. Of course, that's a little bit different if you look at the concentration. So you need a little bit more concentration. You need a little bit more volume in your file. You should have around 2.5 microliters, I think, in your file to really figure out, to be able to inject 1 nanogram. I don't know exactly the right concentration, so I can get back to you about that. I think that was mainly all the answers about what I could say about it.
Okay. We do have another question coming in. Congratulations, great presentation. I would like to know if you're considering studying glycoprofile in exosomes.
Wow. I'm not really familiar with exosomes, but I think in our lab we're quite capable to analyze many different samples and get a glycoprofile out of that. So if you're really interested in that, I think we could really consider to do something like that. It should be, I think, able to do that.
Great. We do have another question. What is the lowest volume you can inject from CESI MS?
Yes. So currently CESI just put some nanofiles on the market, and they're really great because you can inject from really low volumes. 5 microliter has been validated. But they have also tested that you can already do multiple injections of just 1 microliter in your file. But this has not been validated really yet, but it is possible. You get good results with that.
Okay, thank you. We have another question. Great presentation. What about breast cancer and this procedure? Looking forward to incorporating glycosylation analysis in studies. And will the recorded presentation be available?
Yes. So that's indeed really interesting. Breast cancer is also interesting. We know that there also glycosylation can play an important role. However, for breast cancer, we are busy with that in our own lab, only it's not my project yet. So what I could tell about that, for the prostate cancer, we really have a specific glycoprotein that might be interesting for us. For breast cancer, it might be that there are many different glycoproteins that could be interesting. So you need to have a little bit of a distinguishment, because if you want to analyze everything, you kind of get an overload of information. So you would like to focus on one glycoprotein. At least that's something that I would suggest. Let's have a look. So yeah, I think it's really interesting to see also for breast cancer. So as I already said, we're already busy in our lab to also investigate that, because we think glycosylation plays an important role with many, many different diseases. And as I believe this presentation will be available for even 6 months after this date. So you should be still able to see it.
Yes, that is correct. Guinevere, LabRoots is going to be notifying all attendees today when the webcast is available for on-demand replay, and it will be available through December of 2016. So we would invite anybody watching this presentation today to forward that announcement to colleagues they have that didn't get a chance to tune in live today. And we do have another question. What MS instruments can CESI MS be coupled to? And do you know what MS systems you can use DEN gas with?
Yes. So what I've understood, so mainly I use worker systems as mass specs. I also know that we can use, of course, sialic systems. And I believe Waters and Thermo is also able to use CESI MS. For the DEN gas, it's a little bit more interesting because, of course, I performed it on my own Bruker system. But I think it should be rather easy because the principle is rather easy. Just add the dopant-enriched nitrogen gas. You need to just fill your source with this gas. So I think it should be rather easy to apply it also in the other MS systems. But of course, this also needs to be validated. So I can't really say anything conclusive about that.
Okay, thank you. And I am looking in our queue. I don't see any more questions coming in right now. Guinevere, did you have any final comments or advice for our audience? We are coming up on time.
Not really. I would say if people still have questions, always you're free to send me an email and I can inform them about that. Some of our images were a little bit less nice in quality, so if they want to have higher resolution, they can also contact me and I can send them a better PDF file with the slides in there.
Okay, thank you very much for that. It's an excellent presentation. If we weren't able to speak directly with anybody in the audience today, we'll be sure to follow up with you. We want to thank our audience for taking part. I want to thank today's presenter as well for joining us here at LabRoots, leading scientific social networking site. Of course, we'd like to thank SciEx for making this webcast possible. For more information on SciEx and what they do, please visit www.sciex.com. As mentioned before, today's webcast will be available for on-demand viewing on our website through December of 2016. We're going to let you know when it's been posted, and we hope you pass that information on to any colleagues who couldn't be with us today. Thank you again for joining us. We hope to see you next time. Goodbye.
Bye.